All right, it's working. Must be because it's hot dog day. National Hot Dog Day, not just local hot dog day. You would think National Hot Dog Day in America would be the day Joey Chestnut eats like 1,000 of them in 10 minutes, right? But that's not National Hot Dog Day. Yeah, 4th of July. Okay, example 8. This is the LCM divided by the LCM method, or as I call it now since I had Chase Waldrop in class many years ago, the lick-em over lick-em method. Man, he just phonetically pronounced it lick-em over lick-em. So it works, the lick-em over lick-em method. So this method is going to work well, of course, when you get the indeterminate form 0 over 0, but when you have a complex or a compound fraction, okay? Complex or compound fraction. Let's take a look. The limit as x goes to 0, you do have a complex fraction because you have a fraction within a fraction, right? It's written as the diagonal, but you have the parentheses, so there's a fraction and there's a fraction, so that's what makes it complex. Now, never not first again, direct sub. If you plug in a 0, you get 1/2 minus a half, that's 0 over 0. If you plugged in and got like 5, that would be the answer. If you plugged in and got like 0 over 5, the answer would be 0. But because we got 0 over 0, we know the function value doesn't exist. The graph has a hole there. We need to find the y value. So who's causing the 0 in the denominator when you plug in a 0? The x. So we need to get rid of that x. Is there a common factor of x right now in both terms in the top? There is not. Do either one of them have a radical? Nope. So that's not going to work. So what we're going to do is we're going to algebraically eradicate the complex fraction. And the quickest, fastest, most efficient way to do that, because there's lots of ways to do that. You could get a common denominator in the numerator and then do state change flip, but that's multiple lines. We're going to multiply by the LCM over the LCM of what I call to be the miniature denominators. Okay, those are your miniature denominators. The big denominator is x, but your miniature denominators are 2 plus x and 2. So what is the least common multiple, the smallest factor grouping that both 2 and 2 plus x go into? If they're co-prime, if they have nothing in common, it's typically their product. Okay? It's typically their product. So that would be 2 times 2 plus x over 2 times 2 plus x. When in doubt, you can use their product. It may not give you the least common multiple, but it'll always give you a common multiple. Now, if you want to put that up a little bit higher, it's really like over 1 in the top. And the reason that could be helpful is because it's kind of an upstairs-downstairs problem. So let me rewrite this so you can see it the first time. If we write this like this, it's a little more obvious that it's a complex fraction. Okay, it's the same. And we're multiplying now by 2 times 2 plus x, really over 1, and then all over 2 times 2 plus x. So the reason we do that is so that in the numerator, if you extend this right here, you can think of this as like an upstairs-downstairs problem. And then above that big green line, that's the upstairs apartment. Okay? And we have bunk beds in the upstairs apartment. And we're trying to get rid of the bunk beds. All right? So here's what we do. We distribute to both terms. Now, of course, when you distribute the 2 times 2 plus x into the first term, what's going to happen with the 2 plus x factor in the bottom bunk and the 2 plus x in the top bunk? They're going to divide out, not cancel. They're going to divide out. Okay? They're going to divide out. And then we're left with what? 2 times the 1 from the top bunks, and that gives us a 2. Okay? So we're upstairs above the big green line. We have a top bunk, bottom bunk, times the top bunk, bottom bunk. The 2 plus x's will divide out in the top bunk and the bottom bunk, leaving this 2 times that 1. Got it? All right? Minus, when we do the same thing to the second term, the 2 in the top bunk and the 2 in the bottom bunk do what? They divide out. Good. Leaving you a 1. And so we're left with a 1 times the quantity 2 plus x. Now, here's where you have to be careful. What is that sign right below that asterisk? It's a minus, and we're left with the quantity 2 plus x. Would that be right? Right. You need parentheses, or you distribute as you write it down. So that's a common mistake. So be aware of the common mistake. And that takes care of the numerator. You get rid of the complex fraction immediately. And in the bottom, you just multiply straight across. I'll rearrange the factors. That's 2x times 2 plus x. All right, you don't want to distribute the bottom because you still have your x factor exposed, right? And then, of course, we work down. We have to rewrite our limit. So by getting rid of the complex fraction, now I'm left with something in the numerator. Now, guess what happens to here? Some students get excited and they go, ooh, ooh, ooh. First of all, does that work? No, because the quantity 2 plus x is actually a term in the top, not a factor. And that's collateral damage, right? He's not the bad guy to begin with, right? 2 plus x is not causing the 0 when we plug in. So keep your eye on the main target. That's x. But what can we do in the numerator now? Distribute. And if we distribute it, and you could skip this step, if you distribute it in your head, you're going to get 2 minus 2, which is what? 0. And then you're left with negative x, or minus x. So we have minus x now over 2x times 2 plus x. Have we exposed the bad guy in the numerator? Yes, we've run him out of the Afghanistanian caves. All right. And there he is, exposed. There's your 0 over 0 problem. All right. Now we launch the drone, and what happens? They divide out, leaving a what in the top? A negative 1. Okay, cool. So once you get rid of the 0 over 0 problem, what's next? We have made the world safe again for direct substitution. So you plug in, and that's when you no longer need to write the limit. When you plug in, you get negative 1 over 2 times 2, which is 4. So you get negative 1/4. And that's the answer. That's the limit value. That's the y value of the whole for that function. All right, so we cleaned up the complex fraction. We expanded everything that wasn't a bad guy factor, canceled out, divided out. Careful inventory. It's easy to lose track of a negative when you obliterate the x, so make sure you keep track. All right, sound good? So that complex fraction can be written as a diagonal, or it can be written in the numerator, or as in b, it can be written in the denominator. So go ahead and do b on your own. Never not first, direct substitution, though. And I'll go ahead and work it along up here quietly, and we'll compare answers. I hear the police siren. You should call them off, tell them we got the bad guy. Yeah, right, yeah. They would get that joke. If they were calculus cops, they would. And of course, if you've had AB, you know about the calculus cops. We'll meet them later in the year. An elite team of speed trap experts. If you were mesmerized how we wiped out the complex fraction in one step in the previous example, I put this step here with an asterisk. It's an optional thing that you could do if you want to physically distribute. Here's your main division bar, so that's your upstairs, downstairs. If you want to distribute that bottom bunk 6x minus 1 over 1 to each term, you can. That's what I did here. And there's nothing wrong with that. You're just going to have to write everything with the limit up front. And then you could see things dividing out a little bit more readily. But eventually you want to try to work through that in your head, but not at the expense of making a careless mistake. Remember, after you divide out the problem bad guy factors causing 0, 0, direct substitution. All of these methods lead back to direct substitution so far. It's still raining outside this window. Yeah. I wonder if it's raining outside the other window. I'll check. Y'all keep working. It's not? Yep, it's still raining outside this window too. There are at least 2 windows outside of which it is raining at this moment. All right, so if you distribute, and I showed that step down there, the good thing about doing that is you don't have to like mentally divide things out. You can actually get the satisfaction of, right? And so I'll just rewrite the top, 6x times x minus 6 Once those divide out, they should be left with ones. If you correctly multiply by the LCM, you should always end up with ones down here in your denominator. That's how we get rid of the complex fraction. So then we're left with 1 times x minus 6, which is x minus 6. And I don't need parentheses around that, although I could, because there's nothing to distribute, and it's the first term. So if you have them there, that's fine. We'll come back to that. And then plus. So that's a little bit safer with a plus sign instead of a minus sign. And now we're left with 6 times 1 over 1, which is 6. Okay? So if you're at this point and you have the parentheses around the x minus 6, because it's the group that you're left with, this is where you can lose sight of your target and be like, ooh, ooh, ooh. And you do horrible math and you get collateral damage, right? That's not good. If we were approaching 6, x minus 6 would be the bad guy. But we're approaching 0, so we're trying to get rid of this factor, okay? So sometimes parentheses, although they're your best friends, and it's better to have them and not need them, when you don't need them, sometimes they can obscure your vision, right? So if there's nothing to distribute or anything, just drop them. And now, of course, those cancel. And once those cancel, his support, his bodyguard, his protection is gone, and now we can divide them out. And so you can do that in one line, remember, as long as you cancel before you divide out. Now you plug in a 0 to anything that's left, and you get 6 times negative 6, which is negative 36. And that's your answer. So that function, whatever it looks like, has a hole at the ordered pair 0, negative 6, or negative 36, sorry. And that's also the limit value. Okay? So when does Lickum over Lickum work? First, when you get what? 0, 0, and you have a compound or a complex fraction. Yeah. Multiply, expand out, and again, identify the target so you can get rid of the right thing. All right, any questions on Lickum over Lickum? We're only working a couple of examples of each type, really. All right, we have time for one more before lunch here. The next method, for lack of a better term, I just call it the sledgehammer. Anyone ever bought a sledgehammer? You have? Okay, good. Did it come with an instruction manual? No. It did not? No. Okay, so how did you know how to use the sledgehammer then?
The guy in the thick accent that told it to me told me not to smash anything in the town to go out of the town. He was really mad.
The guy with the thick accent said, "Don't smash anything in this town. Go outside of town to smash."
Yeah, it was like a reservation, and I had just broken the other one.
Sweet. So he knew why you were buying a sledgehammer. You were out for destruction, but he wanted to caution you about destroying things in town. Okay. So when you use the sledgehammer, I guess let me try and draw one. There's a handle right here, and then up here you have the sledge, right? And there's, depending on how big, it could be that side. Did you grab it right here and start swinging it back and forth like that? No. Yeah. Okay. Hey, this is not sex ed. This is sledgehammer ed. Okay? No, you didn't grab it there and start swinging, right? You probably knew to grab it right here and start swinging that way, right? Back and forth. Even though there were no instructions. Okay, let's say that never happened. Let's just say it never happened. Even though we're recording it, you could just fast forward right through my inferior artwork. Oh, boy. Okay, we're dealing with rabid teenagers here. Okay. Yeah, how do you use a sledgehammer? Any special skill? No, you just start swinging it, right? Okay, and you destroy things, you make them smaller, you break it down, you destroy things. So this is why I call this the sledgehammer method. I'm not going to do that in AB. I'm not going to tell that story or try to draw it when I do this lesson in AB, okay? So y'all got it. It works well when you get 0 over 0 and when there is obvious math to do. And what do I mean by like obvious math? Yeah, expanding things out or distributing, okay? So you've already plugged in. You've already realized that you got 0 over 0. But none of the other methods that we've worked so far work. There's not a polynomial factor that you could divide out. There's not going to be two terms, at least one with the radical that you can retcon. It's not going to be a complex fraction. It's going to be something that looks differently, all right? So let's try it out on this one here. Now notice we've got the limit as h goes to 0, and in our expression now we have two variables, both x and h. This is going to be common when we get to the next section. Which one do you want to treat as a variable, do you think, in this case? H, right. this down here, and this down here defines the variable of the limit. So if you do have any other variables in here, like the x, my pen's not working, you're going to treat this as a constant. You're going to treat the x as if it were a constant, and h is the variable, okay? So with that in mind, never not first, what should we do? Direct sub. So if you plug in a 0 for h, you're going to get x plus 0, which is x. So you have x squared minus x squared, which is 0, all over 0. All right? So you do get 0 over 0. The bad guy in the bottom is the h factor. He is already exposed in the bottom. We need to divide him out with something in the top. So notice we do have two terms in the top, but there is not an h factor in each of them. There's no radical. There's no complex fraction. So why would this be a sledgehammer? Is there any obvious math to do? What does that 2 mean? Yeah, it means to expand it. So in this case, we're going to FOIL it out. So imagine like picking up a little like 5-pound sledge and dink, hitting it right there on the squared. What's going to happen? You're going to break the parentheses. The 2 is going to fall down, and it's going to crumble into smaller pieces, namely 3 terms, okay? So I just give the sledgehammer the name to expanding things out. So do you remember how to quickly expand a binomial square without having to go off to the side and FOIL it? Yeah. Square multiply double square. Square multiply double square. If you don't double the middle term, it's not going to be right because you're going to get an inside and an outside. When you FOIL, the in and out are the same thing. So you square the first, x squared. You multiply them, x times h, and you double it to get 2xh. So square, multiply double, and then you square the last. Square, multiply double, square. That's how you quickly square binomial. Bless you. And then minus the x squared that's there. So that was a tiny little sledgehammer, right? Dink. It crumbled into 3 terms. Now, is there any obvious math to do? Anything good happening? Your x squareds cancel. Right, things cancel to give you 0. And notice we have 2 things left in the top that are not like terms, but what do they have in them? They each have at least one h in them, and that's our bad guy. So now we will factor it out. We'll still write the limit. And if we factor it out, we get h times 2x plus h, and it's all divided by h. And now we divide out, and I'm running out of room, but now you can plug in a 0 for any h that remains, and we're left with what? 2x. Yeah. So if that has a familiar feel to it, it should, because if you took pre-cal last year, and we're doing this right now in pre-cal, that was what I called my favorite problem. Maybe Mrs. Lincoln called it Mr. Corpy's favorite problem. And that question showed up on the first 3 exams last year in pre-cal. But you set it up yourself, okay? So what this turns out to be later on is something very, very significant when it's related to the function x squared, okay? It ends up being what we call the derivative, if I can spell it right, derivative, there we go, of x squared. Okay, 2x ends up being the derivative of x squared. Okay, and we're going to find it like this first, and then we'll find it a different way that's a lot faster. Okay, but right now we're just evaluating a limit that's given to us. Okay, so in the time that remains, go ahead and do this one. This will have the same feel like my favorite problem. Don't forget direct substitution though first. So I'll work it along here with you. As you're working down, make sure you're still writing the limit each time. Square, multiply, double. If you don't double it, it's not going to work. When y'all did this problem in pre-cal, y'all never had the limit out front. That was the only difference. You set up the ratio without the limit. It was the function evaluated at x plus h, and we'll write that up here. It was the function evaluated at x plus h minus the function itself, which is this guy here. That's f of x. And then it was all over h. And y'all expanded it, which I did on the second line. And remember, once you set it up right with the parentheses up there on f of x, if you did it right, then everything in the top that didn't have h should cancel. So I showed those with symbols. And that does leave the 2xh plus h squared minus 2h. So those three terms all have an h, which you could factor out, leaving 2x plus h minus 2. And then the h's divide out. So back in pre-cal, your final answer would have been 2x plus h minus 2. But this is calculus. And we now have the limit going in front each and every time. Make sure it's there. And then once you get rid of the bad guy factor that's causing 0 over 0, if there is anything left, and there's one h left, you plug in a 0 and you get 2x minus 2. And so as it turns out, you'll learn in the next section that 2x minus 2 becomes the derivative function of the parabola x squared minus 2x plus 1. Yeah?
Why is it only the derivative of that term, not really two?
Oh, because if you put parentheses around here, it's just the way, like if we reverse engineer it, this is blob squared minus 2 blob plus 1. And this is also blob squared minus 2 blob plus 1. So the only difference is in the first function, we're plugging in x plus h for x. And in the second function, we're just plugging in x for x. So if you want to know why that represents the derivative, remember in the next chapter, I'll show where that comes from and why h goes to 0. We define h, remember, to be the distance between those 2 points. And so the secant line becomes the tangent line. So we'll see why that expression gives us the derivative and what the derivative actually means. Okay, but that's what it is. So you don't have to do that right now. Right now, you're just going to be handed a limit, and you're expected to evaluate it. So this is what I call the sledgehammer method. You're just expanding everything out, collecting like terms, and it should work out. The bad guy factor should divide out. Okay, have a fantastic lunch, and we'll pick up with a new parent function after lunch. Woohoo, that's exciting.